Look up at the night sky on a clear evening. You're seeing stars, planets, and the faint, cloudy band of the Milky Way. It's a beautiful sight, but it's also a view into the past. The light from those stars has been traveling for years, decades, even millennia just to reach your eyes. But what if you could peel back those layers of time? What if you could push past the stars, past the galaxies, and look back to the very beginning of everything? What is the absolute oldest thing we can possibly see? The answer is not a star or a galaxy. It's a faint, cold glow that fills every cubic inch of the cosmos, a silent whisper from the moment of creation itself. This is the cosmic microwave background, the universe's oldest light, and it holds secrets about our origin that are more incredible than any science fiction. This ancient light is a direct fossil from the Big Bang. To understand it, picture the universe not as the vast, mostly empty expanse it is today, but as something unimaginably hot, dense, and small. In the first moments after the birth of the cosmos, space was a searing plasma, a thick soup of particles and energy so intense that light itself was trapped, bouncing around endlessly. For nearly 400,000 years, the universe was opaque, a brilliant, blinding fog. Then, in an event cosmologists call recombination, the universe expanded and cooled just enough for atoms to form. Suddenly, light was set free. That first flash, that initial burst of visibility, has been traveling across the expanding universe for almost 14 billion years. We see it today not as a brilliant flash, but as a cold, faint microwave signal that permeates all of space. It is the baby picture of the universe, and we have learned how to develop the film. Over the next while, we're going to unravel 30 astonishing facts about this cosmic afterglow. We will explore how two radio astronomers accidentally stumbled upon it with a massive horn-shaped antenna, a discovery that won them a Nobel Prize. We'll see how tiny, almost imperceptible wrinkles in this light are the blueprints for every galaxy, star, and planet that exists today, including Earth and everyone on it. We'll investigate what this light tells us about the mysterious dark energy that is pulling the universe apart and the invisible dark matter that holds it together. This journey will change how you see the night sky, transforming it from a static painting into a dynamic, evolving storybook, with its very first page written in this ancient, omnipresent light. So, let's begin at the beginning with the oldest story ever told, written in the oldest light we can see. That faint, omnipresent glow is the single most important piece of evidence we have for the Big Bang. Think of it as the dying embers of the universe's most colossal fire. When you sit by a campfire long after the flames have died down, you can still feel the warmth radiating from the glowing coals. The cosmic microwave background is the universe's version of that residual heat. It's the cooled down, stretched out energy that has been traveling across space ever since the cosmos became transparent for the very first time. This momentous event happened when the universe was about 380,000 years old. Before that, it was far too hot and dense for light to travel freely. It was a swirling, opaque fog of plasma where photons of light were constantly bouncing off a dense soup of electrons. But as the universe expanded, it cooled, and when it reached a temperature of around 3,000 degrees Celsius, a fundamental shift occurred. Electrons combined with protons to form the first atoms, mostly hydrogen. Suddenly, the fog cleared. The universe went from being opaque to transparent in what we might call the universe's first true dawn. In that instant, the light that had been trapped for all those millennia was finally set free, and it began its journey across the cosmos. That initial burst of light, once blazingly hot, has been traveling for almost 14 billion years, and in that time, the universe itself has expanded exponentially, stretching the very fabric of space. This expansion has stretched the wavelengths of that primordial light, shifting it from the visible spectrum all the way down to the microwave part of the spectrum. What was once a brilliant, uniform glow of white-hot light is now a cold, faint whisper with a temperature of just 2.7 degrees above absolute zero. It is a fossil, but a perfectly preserved one. By detecting and studying this signal, our telescopes are essentially looking directly back to that wall of last scattering, that moment of recombination, giving us a baby picture of the cosmos that is astonishingly detailed. The story of how this ancient light was found reads more like a detective novel than a scientific breakthrough. In the mid-1960s, two young radio astronomers, Penzias and Wilson, were working at Bell Labs in New Jersey. They were using a gigantic, extremely sensitive horn-shaped antenna, originally built for satellite communication, to study radio waves from our own galaxy. But their work was plagued by a persistent, maddening problem. No matter where they pointed the antenna, they couldn't get rid of a faint, constant hum of microwave noise. It was there day and night in every direction, and it was interfering with the signals they actually wanted to measure. They were meticulous scientists, so their first assumption was that the fault lay with their equipment. They checked every connection, every component. They even suspected the pigeons that had taken up residence inside the large horn of the antenna. Convinced that what they called a white dielectric material, a polite term for pigeon droppings, was causing the interference, they carefully evicted the birds and scrubbed the antenna clean. Yet, to their immense frustration, the annoying hum remained. It was an enigma, a signal with no apparent source that simply wouldn't go away. Meanwhile, just 30 miles away at Princeton University, a team of physicists led by Robert Dicke had been building a detector specifically to find this very signal. They were working on a theory that if the Big Bang had indeed occurred, the entire universe should be filled with a cool, leftover glow. Unbeknownst to Penzias and Wilson, they were holding the very evidence the Princeton team was searching for. The breakthrough came through a fortunate conversation. After exhausting all other explanations, Penzias happened to call a fellow astronomer who mentioned the Princeton group's theoretical work. It was a moment of stunning realization. The noise they had been trying so hard to eliminate wasn't a technical flaw or a result of pigeons. It was the echo of creation itself. They had accidentally stumbled upon the cosmic microwave background. This serendipitous discovery was the final, crucial piece of evidence that transformed the Big Bang theory from a compelling idea into the cornerstone of modern cosmology. It was so monumental that in 1978, Penzias and Robert Wilson were awarded the Nobel Prize in Physics for their accidental detection of the universe's oldest light. So, Penzias and Wilson had detected the signal, but what did their sensitive antenna actually reveal about its character? The most immediate and striking feature was its incredible uniformity. As they painstakingly pointed their antenna in different directions, the intensity of the microwave noise, which corresponds to its temperature, was virtually identical everywhere they looked. Today, with vastly more sensitive instruments, we've measured this temperature with exquisite precision. The cosmic microwave background glows at a bone-chilling 2.725 degrees above absolute zero, which is about -270 degrees Celsius. This means that if you could perceive microwaves with your eyes, the entire sky, from horizon to horizon, would appear to glow with an almost perfectly even, faint light. This profound smoothness tells us something fundamental about the infant universe. It was in a state of what physicists call thermal equilibrium, a condition where energy has had enough time to distribute itself evenly, like a cup of coffee that has been stirred and has settled into a single, uniform temperature. For the early universe to be this smooth, every part of it must have been in contact with every other part, allowing heat to flow and balance out the temperature. And this is where the puzzle emerges, a problem so significant it became known as the horizon problem. Think about the observable universe as it was at 380,000 years old. Even at that young age, it was already vast. According to the standard Big Bang model, There hadn't been enough time since the beginning for light or any influence to travel from one distant region to another to even out their temperatures. It's as if you walked into a massive concert hall and found thousands of people who had never met, all humming the same note in perfect pitch without any prior communication. How could regions of the universe that were seemingly never connected somehow agree to be at the exact same temperature? This magnificent uniformity, the very hallmark of the CMB, was actually a profound mystery. It suggested that our understanding of the universe's earliest moments was incomplete, that some mechanism must have acted to synchronize the entire cosmos, creating the smooth canvas upon which the later universe would be painted. Yet for all its profound smoothness, that baby picture of the universe is not featureless. If it were perfectly uniform, we wouldn't be here to talk about it. The incredible breakthrough that followed the initial discovery was the detection of the tiniest of imperfections in this cosmic canvas. While the background temperature is astonishingly even, it is not perfectly so. Precise measurements from satellites like the Cosmic Background Explorer, or COBE, revealed minuscule variations, tiny patches of the sky that are ever so slightly warmer or colder than the average. We're talking about differences on the scale of just 1 part in 100,000. To grasp how subtle that is, imagine a perfectly smooth sheet of glass stretched across the entire sky. The variations in the cosmic microwave background would be equivalent to the thickness of a single sheet of paper lying on that vast plane. These tiny ripples, known as anisotropies, are the most important fingerprints in the entire cosmos. They are the gravitational seeds from which everything we know, every galaxy, every star, every planet, would eventually grow. These minute temperature differences are a direct map of density fluctuations in the early universe. A slightly warmer spot corresponds to a region that was ever so marginally denser, packed with just a few more particles. A slightly cooler spot marks a region that was a little bit emptier. In the fierce competition of gravity, those tiny advantages made all the difference. Over hundreds of millions of years, gravity relentlessly amplified these small differences. The denser regions, with their slightly stronger gravitational pull, began to attract more and more matter from their surroundings. The slightly warmer, denser patches grew steadily denser, collapsing under their own weight to form the first vast clouds of gas that would become galaxies. The cooler, emptier regions, in turn, evolved into the great cosmic voids we see today. So when you look at a modern, full sky map of the cosmic microwave background, covered in a speckled pattern of red and blue spots, you are not just looking at a temperature chart. You are looking at the original architectural blueprint for the entire large-scale structure of the universe. Every cluster of galaxies, every filament of dark matter, and even our own Milky Way has its ultimate origin traced back to one of these infinitesimal wrinkles in the fabric of the newborn cosmos. This idea of the cosmic microwave background as a baby picture is more than just a poetic metaphor. It is a literal, physical reality. The light that our satellites like Planck and WMAP collect has been on an uninterrupted journey across the cosmos for over 13.8 billion years. When we detect a photon from the CMB, we are intercepting a messenger that has been traveling since the universe was a mere 380,000 years old. To appreciate how young that is, consider the universe's current age of nearly 14 billion years. Capturing an image of the universe at that moment is like having a single photograph of a person taken when they were just 1 day old. It is our only direct glimpse into the universe's infancy, a snapshot frozen in time before the first stars or galaxies had even begun to form. This isn't an artist's impression or a computer simulation. It is a genuine photograph of the cosmos at its most primitive state. The surface we are seeing, often called the surface of last scattering, is a wall in time. It is the farthest back in history we can possibly see with light. Before that wall, the universe was an opaque, glowing fog, and no telescope will ever be able to peer beyond it. This makes the CMB the ultimate boundary of observational science, our final frontier for directly witnessing the past. By studying this ancient snapshot, cosmologists can measure the fundamental properties of the infant universe with incredible precision. We can determine its exact temperature, its rate of expansion, its overall density, and its composition. It tells us that the early universe was far simpler than the complex web of galaxies we see today, a nearly uniform, hot soup of hydrogen and helium plasma, seething with the tiny quantum seeds that would one day become everything. Every time a new, more sensitive map of the CMB is released, it's like getting a higher resolution copy of that first baby picture, allowing us to see finer details and understand more deeply the initial conditions from which our entire cosmic story unfolded. Now, let's consider the transformation this ancient light has undergone. When the universe first became transparent, the cosmic microwave background wasn't cold or faint, and it certainly wasn't in the microwave part of the spectrum. In that first brilliant moment of liberation, the entire cosmos was flooded with an intense, searing glow of white-hot light. If a human eye could have been present, the sky would not have been dark. It would have been a blinding, uniform orange-white, similar to the surface of a star, because the universe itself had a temperature of around 3,000 degrees Celsius. This was the original color of the universe, so how did that blazing, visible and ultraviolet light become the cold microwave signal we measure today? The answer lies in one of the most fundamental and mind-bending consequences of an expanding universe: cosmological redshift. Think of a wave of light traveling through space as having a specific wavelength, like the distance between two crests of a wave in the ocean. Now imagine that as this light wave travels, the very fabric of space itself is stretching. The space between those wave crests is literally getting longer. This stretching directly increases the wavelength of the light. The longer the wavelength, the less energy the light carries, and this shift towards longer, lower energy wavelengths is what we call redshift. It's not that the light is physically tired from its long journey. It's that the expanding universe has been stretching it out for billions of years. In a very real sense, the light itself has been cosmologically cooled by the expansion of space. The initial visible light over an almost unimaginable journey of 13.8 billion years has been stretched by a factor of about 1100. Its wavelength has been pulled from the tiny scale of visible light, measured in millionths of a meter, all the way to the centimeter scale of microwaves. This is why a signal that began as a fiery glow is now detected by our instruments as a faint whisper with a temperature of just 2.7 degrees above absolute zero. This incredible stretching is a direct and measurable testament to the amount the universe has expanded since its infancy, forever imprinting the history of cosmic expansion onto the light itself. Confirming the precise nature of this ancient glow was the crucial next step, and for that, science had to reach beyond the Earth's atmosphere. While Penzias and Wilson's groundbreaking discovery proved the signal existed, it was like hearing a single, constant note from a symphony. To truly understand the music of the early universe, we needed to hear every instrument to map the entire celestial orchestra. That required getting above the murky interference of our own planet's atmosphere, which blocks and distorts much of the faint microwave light. The mission to do this was the Cosmic Background Explorer, or COBE, a satellite that would change cosmology forever. Launched by NASA in November 1989, COBE was designed with one overarching goal: to measure the cosmic microwave background with a level of precision that was impossible from the ground. It carried a suite of instruments, but one of its most critical tasks was to answer a very specific question about the light's quality. According to the Big Bang theory, the CMB shouldn't just be any kind of radiation. It should have the signature of a perfect blackbody. A blackbody is an idealized object that absorbs all radiation that hits it and then re-emits it with a spectrum that depends only on its temperature, not on what it's made of. Think of the glowing element on an electric stove. As it heats up, it first gives off invisible infrared warmth, then glows a dull red, and if it could get hot enough without melting, it would become white hot. The color and intensity of its glow at each wavelength follow a precise, predictable curve dictated solely by its temperature. The early universe at the moment of recombination was essentially a perfect glowing blackbody. The Big Bang theory made a firm prediction. After being stretched by the expansion of the universe, the CMB we see today should still exhibit this perfect blackbody curve, corresponding to a temperature of about 2.7 degrees above absolute zero. Any significant deviation from this perfect curve would have been a major problem for the theory. When COBE instruments, specifically the Far Infrared Absolute Spectrophotometer or FIRAs, looked at the sky, the results were breathtaking. The data points aligned with the predicted blackbody curve with an accuracy so incredible it has been called the most perfect blackbody spectrum ever measured in nature. The match was exact to within 1 part in 10,000. This wasn't just a confirmation, it was a resounding validation. The universe's oldest light had exactly the properties the Big Bang model said it must have, a triumph that solidified our understanding of the cosmos's hot beginning. But COBE contributions didn't stop there. While one instrument was confirming the perfect thermal nature of the background, another was tasked with looking for the tiny imperfections within it. The differential microwave radiometer, or DIMR, was designed to scan the entire sky and create a detailed map of the CMB's temperature, looking for those all-important anisotropies, the tiny variations that would prove the universe wasn't completely smooth. For the first year, the data from COBE showed exactly what Penzias and Wilson had found, an astonishingly uniform temperature across the heavens. The signal was so smooth that the initial maps appeared featureless. It wasn't until the team had collected enough data to reduce the noise to an incredibly low level that the truth finally emerged. In 1992, the COBE team, led by scientists George Smoot and John Mather, announced a historic discovery. They had found the seeds of cosmic structure. The map they revealed to the world showed the sky not as a perfectly uniform sheet, but as a mottled canvas of tiny temperature fluctuations. These fluctuations were incredibly subtle variations of only about 1 part in 100,000, but they were real and they were everywhere. This was the moment cosmology grew up. The discovery was so significant that George Smoot famously said, "If you're religious, it's like looking at the face of God." The COBE map was the first ever baby picture of the universe, and it showed the initial ripples that gravity would later sculpt into the grand tapestry of galaxies. For their monumental work, John Mather and George Smoot were awarded the Nobel Prize in Physics in 2006, cementing COBE legacy as one of the most important scientific missions of all time. It provided the first detailed look at the primordial blueprint and set the stage for even more ambitious explorers to follow. Following COBE monumental first map, the next chapter in our cosmic cartography required an even sharper lens. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, was designed to be that lens. Where COBE had given us the first grainy, baby picture of the universe, WMAP was tasked with creating a high-definition portrait. Its mission was to measure the tiny temperature differences in the cosmic microwave background with a resolution more than 30 times sharper than its predecessor. To achieve this, WMAP was sent to a special vantage point far from Earth, a stable orbital location called the second Lagrange point, or L2, roughly 1.5 million kilometers away. From this quiet, thermally stable spot in space, far from the interference of Earth's heat and radio noise, WMAP could scan the entire sky with incredible sensitivity, patiently collecting data for 9 years. The map it produced was nothing short of revolutionary. Instead of the blurry speckles seen by COBE, WMAP full sky image revealed the cosmic microwave background in exquisite detail, showing a complex, fingerprint-like pattern of hot and cold spots of various sizes. This wasn't just a prettier picture, it was a rich data set encoded with the universe's deepest secrets. Scientists could now measure the statistical properties of these temperature fluctuations, how many large spots versus medium or small spots there were, with phenomenal precision. This pattern is like a cosmic barcode, and reading it allowed cosmologists to determine fundamental properties of the universe with an accuracy that was previously unimaginable. WMAP data allowed us to announce the universe's age with remarkable confidence, 13.77 billion years, with an uncertainty of just a few tens of millions of years. It precisely measured the composition of the cosmos, revealing that ordinary matter, the atoms that make up stars, planets, and us, accounts for only about 4.6% of the total density of the universe. The rest, it confirmed, is the mysterious dark stuff, about 24% dark matter and a dominating 71% dark energy. Perhaps one of its most profound findings was about the geometry of the universe itself. According to Einstein's theory of general relativity, the overall density of matter and energy determines the shape of spacetime. WMAP measurements showed that the universe is geometrically flat to within a tiny margin of error. This doesn't mean it's like a sheet of paper, but rather that parallel lines will never meet or diverge over cosmic distances, and the angles of a triangle always add up to 180 degrees. This flatness is a critical prediction of the inflationary theory, which proposes a period of hyper-fast expansion in the universe's first fraction of a second. WMAP's incredibly precise dataset became the bedrock for what is now the standard model of cosmology, known as the lambda cold dark matter model, or lambda CDM. In this model, lambda represents the cosmological constant associated with dark energy, and CDM refers to the cold, slow-moving dark matter that governs the growth of structure. WMAP didn't just add details to our picture of the cosmos. It provided the rigorous, quantitative framework that firmly established our modern understanding of the universe's origin, evolution, and ultimate fate. If COBE gave us the grainy baby picture and WMAP provided the high-definition portrait, then the European Space Agency's Planck satellite was tasked with creating an ultra-high-definition, forensic-level image of the infant cosmos. Launched in 2009, Planck was a technological marvel, representing the absolute pinnacle of our ability to observe the universe's first light. Its mission was simple in goal but breathtaking in ambition: to measure the cosmic microwave background with a sensitivity and resolution that would dwarf all previous efforts. Where WMAP instruments were cooled to a chilly 95 Kelvin, Planck's detectors were chilled to a fraction of a degree above absolute zero, just 0.1 Kelvin. This incredible cold was necessary to make the satellite itself vastly quieter than the faint signal it was trying to detect, allowing it to perceive the subtlest whispers in the cosmic static. Planck scanned the entire sky not just once, but multiple times over 4.5 years, collecting an unprecedented treasure trove of data. The map it produced was our sharpest view yet, revealing the speckled pattern of primordial fluctuations with a resolution so fine it was like going from a standard television image to the clearest IMAX film imaginable. Every tiny dot and subtle variation was captured with stunning clarity, providing cosmologists with the most detailed cosmic barcode ever recorded. This extraordinary level of detail was not just for show, it allowed scientists to perform a kind of cosmic blood test on the universe, measuring its vital signs with near-perfect precision. By analyzing the intricate statistics of the hot and cold spots, their sizes, their distribution, and how they correlated with one another, Planck could put our leading cosmological models through the most rigorous test imaginable. The results were a triumph for the standard lambda cold dark matter model, but they also refined it in crucial ways, tightening the constraints on its parameters to an astonishing degree. For instance, Planck's data allowed scientists to pin down the universe's age with incredible confidence, 13.8 billion years, a figure that is now the gold standard in cosmology. It also delivered the most precise census of the cosmos's composition to date, confirming that ordinary matter, the stuff of stars and planets, makes up a mere 4.9% of the universe. Dark matter comprises 26.8%, and dark energy, the mysterious force driving the accelerated expansion, accounts for 68.3%. But Planck's sharp vision did more than just confirm what we already knew. It also began to reveal tiny, intriguing anomalies. For example, the satellite confirmed a strange asymmetry in the sky. One hemisphere of the universe appears very slightly warmer than the other, a feature that the standard model struggles to fully explain. It also found that the universe's large-scale fluctuations are about 10% less intense than the model predicts. These aren't discrepancies that overturn our understanding, but they are tantalizing hints. They are like finding a few unexpected brushstrokes on an otherwise familiar masterpiece, suggesting that there may be new physics waiting to be discovered, subtle forces or properties from the universe's first moments that we have not yet begun to comprehend. Planck's legacy, therefore, is dual. It provided the most definitive confirmation of our current cosmic story while simultaneously opening new, deeper questions for the next generation of explorers to solve. One of the most mind-bending revelations from studying the cosmic microwave background is the answer it provides to a question humanity has pondered for millennia: what is the shape of the cosmos? For centuries, we imagined the universe as a vast, perhaps infinite, three-dimensional stage. But Einstein's theory of general relativity introduced a radical idea. This stage itself could be curved by the matter and energy within it. The universe as a whole could have a global geometry. It could be positively curved like the surface of a sphere folding back in on itself. It could be negatively curved like a saddle bending away in all directions. Or against all odds, it could be perfectly flat. The patterns imprinted on the CMB act as the ultimate arbiter of this cosmic geometry, and the results are as definitive as they are profound. By meticulously analyzing the size of the temperature fluctuations, the hot and cold spot scientists can perform a test that functions like a cosmic ruler. Imagine you are looking at a grid painted on a surface. If that surface is flat like a tabletop, the lines of the grid will appear straight and the angles of the squares will be perfect 90 degrees. But if the surface is curved like a globe, the grid lines will appear to bend and the shapes will distort. The early universe, at the moment of recombination, produced sound waves traveling through the hot plasma. These waves had a characteristic size known as the acoustic scale, which was set by the physics of the primordial soup. This scale became frozen into the CMB as a preferred size for the temperature fluctuations. When satellites like WMAP and Planck measured the statistical distribution of these spots, they were looking for this characteristic scale. The observed angular size of these spots on the sky tells us directly about the geometry of the universe. If the universe were positively curved like a sphere, light rays from these spots would converge, making them appear larger than they truly are. If it were negatively curved like a saddle, the light would diverge, making the spots appear smaller. The data from both missions delivered a stunningly clear result. The spots appear at exactly the angular size predicted for a perfectly flat universe. The geometry of our cosmos on the largest scales is Euclidean. This doesn't mean the universe is a flat, two-dimensional plane. It means that on cosmic scales, parallel lines will never meet or diverge, and the angles of a triangle will always add up to 180 degrees. This finding of flatness has monumental implications, the most critical being that it dictates the precise density of the universe. There is a specific critical density required for a flat universe, a delicate balance between the expansion rate and the gravitational pull of all the matter and energy inside. The fact that we live in a flat universe means the actual density of the cosmos is incredibly close to this critical value. This balance is so perfect, so unlikely to have occurred by chance from the chaotic conditions of the Big Bang. that it became one of the strongest pieces of evidence for a pivotal event in the very first instance of time, cosmic inflation. This cosmic blueprint, this incredibly detailed baby picture, does far more than just show us what the early universe looked like. It allows us to perform the ultimate forensic accounting, to take a complete and precise inventory of everything that makes up our entire reality. By carefully reading the subtle patterns in the cosmic microwave background, scientists have been able to calculate the exact recipe of the cosmos, and the results are both humbling and astonishing. The universe, it turns out, is overwhelmingly made of substances that are completely alien to our everyday experience. The atoms that form everything we can see and touch, the stars, the planets, the air we breathe, and our own bodies account for a mere 5% of the total content of the universe. This ordinary matter, which has been the sole focus of science for centuries, is actually just the cosmic icing on a very strange cake. The remaining 95% is composed of two mysterious, invisible components, dark matter and dark energy, whose natures remain one of the greatest puzzles in all of physics. So, how can a snapshot of the universe at 380,000 years old tell us what it's made of today, over 13 billion years later? The answer lies in how each component of the cosmic recipe influenced the growth of those tiny seeds we see in the CMB. Think of the early universe as a pond on a perfectly calm day. If you toss a handful of pebbles into the water, ripples will spread out. The exact pattern of those ripples, their size, their spacing, how quickly they fade depends on the properties of the water itself. Is it thick and viscous or thin and watery? The CMB's pattern of hot and cold spots is the fossilized ripple pattern from the early universe, and by analyzing its statistical properties, we can deduce what the cosmic water must have been made of to produce exactly that pattern. Ordinary matter, the atoms we know, interact strongly with light and pressure. In the dense early universe, this created powerful sound waves that traveled through the plasma, leaving a very specific signature in the size of the temperature fluctuations. Dark matter, on the other hand, is thought to be a heavy, slow-moving particle that does not interact with light at all. It only feels the force of gravity. This means that while ordinary matter was being pushed around by radiation pressure, dark matter was already quietly clumping together under its own gravity, providing gravitational wells that the ordinary matter would later fall into. The relative amounts of ordinary matter and dark matter determined how pronounced these gravitational wells were and how the sound waves propagated, imprinting a characteristic peak in the distribution of spot sizes. By measuring the location and height of these acoustic peaks with satellites like Planck, cosmologists can calculate the precise ratio of the two. The result is clear and consistent. Dark matter outweighs ordinary matter by a factor of about 5 to 1, making up roughly 27% of the universe. The most dramatic revelation, however, concerns the remaining 68%, dark energy. This bizarre component doesn't show up directly in the CMB snapshot from the infant universe. At that time, the universe was very dense and gravity's pull was dominant, slowing down the expansion. Dark energy's signature is written not in the initial conditions, but in how those conditions appear to us from a distance of 13.8 billion years. The geometry of the universe, which we know is flat, acts as a cosmic magnifying glass. The apparent size of the fluctuations on the sky depends on the total distance the light has traveled to reach us, which in turn depends on the entire history of cosmic expansion. If the universe had continued to expand at a slowing rate due to gravity, the light's journey would have been different and the pattern of spots would appear larger to us. The fact that the spots appear exactly the size predicted for a flat universe tells us that something must have caused the expansion to accelerate later in cosmic history, stretching the light's path in a specific way. This something is dark energy. Its presence and overwhelming abundance are the only way to reconcile the pristine flatness of the universe seen in the CMB with the observed accelerated expansion we measure today from distant supernova. This cosmic recipe, 5% atoms, 27% dark matter, and 68% dark energy, is arguably the most profound and significant legacy of CMB research. It is a stark reminder that our familiar, visible world is just a tiny fraction of a much larger and overwhelmingly mysterious cosmic reality. Now, this perfect flatness and astonishing uniformity presented a profound puzzle for the original Big Bang theory, one that demanded a truly radical solution. How could the universe be so perfectly balanced and smooth if it had simply expanded from a chaotic, hot singularity in a steady, stately manner? The answer emerged in the early 1980s with a theory so powerful it has become a cornerstone of modern cosmology: cosmic inflation. This idea proposes that the universe didn't just begin with a bang, but with a bang followed immediately by a staggeringly violent growth spurt. In the first infinitesimal fraction of a second, perhaps around 10 to the power of -36 seconds after the Big Bang, the universe underwent a period of exponential expansion, inflating from a subatomic speck to something macroscopic faster than the speed of light. This wasn't expansion through space, but the rapid stretching of space itself, a process driven by a mysterious repulsive energy field often called the inflaton. This inflationary epoch solved the classic cosmological problems in one elegant stroke. The horizon problem, the mystery of how disconnected regions of the sky could have the same temperature, was resolved because before inflation, the entire observable universe was a tiny, quantum-scale volume where everything was in thermal contact. It was all causally connected. Inflation then blew up this tiny, uniform patch to become the entire cosmos we see today. The flatness problem, the question of why the universe's density is so perfectly fine-tuned, found its answer because inflation acted like a cosmic magnifier, stretching the fabric of spacetime so enormously that any initial curvature would have been flattened out, just as inflating a balloon makes its surface appear flatter and flatter from any local viewpoint. In this framework, the incredible large-scale smoothness and geometric flatness we measure are not mysterious coincidences. They are the direct and predictable outcomes of this primordial inflationary burst. But a grand theory like inflation must make testable predictions, and this is where the cosmic microwave background becomes the ultimate proving ground. Inflation doesn't just predict a smooth and flat universe, it also provides a mechanism for creating the seeds of all structure. The theory posits that the violent expansion of spacetime would have magnified tiny quantum fluctuations, minuscule ripples in the fabric of reality that were present at the quantum scale, stretching them to astronomical sizes. These amplified quantum jitters became the density variations that we now see as the temperature anisotropies in the CMB. This is a breathtaking connection. The largest structures in the universe, galaxy clusters and vast cosmic voids, have their origin in the unpredictable, fuzzy world of quantum mechanics. The specific pattern of these fluctuations, as mapped by Planck and WMAP, matches the predictions of the simplest inflationary models with remarkable accuracy. The statistical distribution of the hot and cold spots, how many large ones versus small ones there are, aligns precisely with what inflation theorists calculated. Furthermore, inflation leaves a more subtle fingerprint in the CMB's polarization. When light waves scatter off particles, they can become polarized, meaning their electric fields vibrate in a preferred direction. The moment of recombination, when the CMB was set free, was a massive scattering event. Inflationary models predict that the violent stretching of spacetime during that initial epoch would have generated gravitational waves, ripples in the fabric of spacetime itself. These primordial gravitational waves would have jostled the primordial plasma, creating a specific swirling pattern in the polarization of the CMB light, known as B-mode polarization. Detecting this signature would be considered a smoking gun for inflation. While there have been tentative signals and intense searches, a definitive, uncontroversial detection of these primordial B modes remains one of the holy grails of cosmology. The fact that the temperature fluctuations so exquisitely match inflationary predictions is considered strong, albeit indirect evidence. It's like finding footprints at a crime scene that perfectly match a suspect's shoes. It's compelling evidence, but finding the suspect's DNA would be the clincher. The quest for that DNA, the B-mode polarization from gravitational waves, continues to drive the design of ambitious new telescopes aimed at the CMB, pushing our observational capabilities to their very limits in the hope of confirming the universe's most dramatic moment. The story of the universe's first light is not just a visual one, it's also a sonic symphony, a record of the very first sounds ever produced. To understand this, we need to travel back to that searing plasma before the moment of recombination. This wasn't a silent, empty space. It was a roiling, chaotic medium where particles of light, photons, were locked in a constant, fierce dance with the building blocks of matter, primarily protons and neutrons, which cosmologists collectively call baryons. In this incredibly dense and hot soup, these particles were so tightly bound that they behaved almost as a single fluid. Now, introduce the two fundamental forces at play: gravity and radiation pressure. Gravity, always the great unifier, constantly tried to pull the plasma into denser clumps, but it had a powerful opponent. The intense radiation from the photons created an enormous outward pressure, pushing back against gravity's inward pull. This created a cosmic tug-of-war, a relentless cycle of compression and expansion. When gravity managed to compress a region of the plasma, it grew denser and hotter, which increased the radiation pressure. This intense pressure then acted like a spring, rebounding and pushing the material outward. As the plasma expanded, it cooled and became less dense, which allowed gravity to once again gain the upper hand and pull it back together. This back-and-forth action set the entire early universe ringing like a bell. These oscillations were not random noise. They were organized, predictable sound waves propagating through the primordial fluid. The most important type were the standing waves, similar to the fundamental tones a bell produces when struck. These acoustic oscillations had a specific, characteristic scale determined by the speed of sound in that early plasma. And here's a fascinating detail. The speed of sound in that hot, dense medium was incredibly fast, close to 57% the speed of light. This means a pressure wave could travel a considerable distance in the few 100,000 years before recombination. But there was a strict deadline: the moment the universe cooled enough for atoms to form. At that instant, the music stopped abruptly. The photons decoupled from the matter and streamed freely across the universe, while the baryons, suddenly freed from the relentless push of radiation, were left frozen in place. The key here is that the waves were captured at different phases of their oscillation. Some regions were caught at the point of maximum compression, where gravity had pulled the plasma into its densest, hottest state. Other regions were captured at the moment of maximum rarefaction, where the radiation pressure had pushed the material outward, creating a cooler, emptier area. This is the brilliant connection to the cosmic microwave background. Those tiny temperature fluctuations we see as hot and cold spots are not just random wrinkles, they are the direct frozen imprint of these sound waves. A hot spot in the CMB corresponds to a region of the plasma that was caught at the peak of compression. A cold spot marks a region frozen at the moment of maximum expansion. When scientists analyze the CMB map, they don't just see a random pattern, they see the fossilized record of a universe filled with sound. By measuring the statistical distribution of these spots specifically, looking at the preferred sizes of these hot and cold regions, cosmologists can identify a distinct peak in the data. This peak represents the most common wavelength, the fundamental tone of the cosmic bell. It's the signature of a sound wave that had just enough time to travel from its origin to the edge of a growing overdensity and back again once before the music stopped at recombination. This distance is known as the sound horizon, and its size, imprinted on the CMB, serves as a fantastically precise standard ruler. It allows us to measure fundamental properties of the universe with the same kind of precision that a musician uses a tuning fork. The fact that we can detect this acoustic peak so clearly is a stunning confirmation of our understanding of the physics of the early universe, turning the sky into a cosmic musical score that we have learned to read. This concept of the universe's first sound waves doesn't just end with the cosmic microwave background. It has a profound and direct echo in the universe we see today. Those frozen sound waves, known as Barrian acoustic oscillations, created a lasting imprint not only in the ancient light, but also in the varied distribution of matter across the cosmos. Think of it like this: when the music stopped at recombination, the waves didn't just vanish. They left behind a distinct shell-like pattern. Each of those initial overdense regions, the seeds of future galaxies, was surrounded by a spherical shell of matter that had been pushed outward by the last pulse of radiation pressure. Once the photons left, this pattern was set in stone, or rather, set in space-time. As the universe continued to expand and gravity worked over billions of years, this faint, fossilized ripple traveled with it. Galaxies didn't form randomly. They formed preferentially at the sites of those original overdense regions, which were now each sitting at the center of a vast, subtle, spherical density wave. This gives astronomers an incredible gift, a standard ruler etched across the entire sky. The distance that a sound wave could travel from the beginning of the universe until recombination. The sound horizon is a fixed length about 500,000 light-years across at that time. Because we understand the physics of the early universe so well, we know this exact scale. As the universe expanded, this ruler stretched along with it. Today, that same scale has grown to span nearly 500 million light-years. This means that if we look out at the large-scale structure of the modern universe, we should see a subtle preference for pairs of galaxies to be separated by this specific distance. It's as if every galaxy cluster in the cosmos sits at the center of a giant, invisible bubble, with a slight statistical excess of other galaxies on the bubble's surface. By conducting massive galaxy surveys like the Sloan Digital Sky Survey, which maps the positions of millions of galaxies, astronomers can indeed detect this signal. They can measure this preferred scale in the distribution of galaxies, and because they know how big the ruler was to begin with, they can use it to measure how much the universe has expanded since the light from those galaxies was emitted. This makes Barrian acoustic oscillations one of the most powerful tools in modern cosmology for probing the expansion history of the universe and the nature of dark energy. It provides a cosmic yardstick that is independent of other methods like supernova, offering a crucial cross-check that gives us tremendous confidence in our measurements of the cosmos's accelerating expansion. When we analyze the detailed map of the cosmic microwave background, we're not just looking at a picture, we are reading a complex musical score. Scientists translate the pattern of hot and cold spots into what's called a power spectrum, which is essentially a graph that shows us the relative strengths of the different notes or frequencies that make up the cosmic symphony. The most striking feature on this graph is the first acoustic peak. This prominent peak represents the most common size or wavelength for the temperature fluctuations we see. It corresponds to the sound waves that had just enough time to complete one full oscillation from compression to rarefaction and back to compression, before the universe became transparent and the music stopped at recombination. Think of it as the fundamental tone of the cosmic bell, the note that resonated most powerfully throughout the primordial plasma. The physical size of this wave, the distance it traveled from its origin to the edge of the overdensity and back again, is known as the sound horizon. At the moment of recombination, this sound horizon had a fixed physical size, about 500,000 light-years across. It was set by the speed of sound in the early universe, which was incredibly fast, and the amount of time available, roughly 380,000 years. Now, here is where cosmology performs a truly elegant piece of detective work. We know how big that sound horizon was in actual light years at the time the CMB was emitted. But when we look up at the sky today, we don't see it in terms of its true physical size. We see it as an angular size, how many degrees it takes up on the celestial sphere. This is no different from noticing that your thumb, held at arm's length, covers a certain angle of your field of view. If you move your thumb closer, it covers a larger angle. Move it farther away and it covers a smaller one. The apparent angular size of an object of known true size tells you its distance. The CMB's first peak provides us with the ultimate standard ruler. We know its true size from physics, and we can measure its apparent angular size on the sky with incredible precision using satellites like Planck. This measurement is absolutely fundamental. If the universe were positively curved like a sphere, the paths of light would bend inward, making the ruler appear larger than it should, just like the lines of longitude on a globe appear to converge. If the universe were negatively curved like a saddle, the light paths would diverge, making the ruler appear smaller. The data delivers a stunningly clear verdict. The angular size of the first acoustic peak is exactly what we would expect for a perfectly flat universe. The cosmic ruler appears with a precise scale that confirms the geometry of our cosmos is Euclidean on the largest scales. This single measurement, more than any other, pins down the flatness of the universe and, by extension, its total density. It tells us that the combined energy density of all the components of the cosmos, ordinary matter, dark matter, and dark energy, adds up to the critical density required for a flat geometry. This finding is a monumental triumph for the inflationary Big Bang model, which predicts this precise flatness as a natural outcome of the universe's initial exponential expansion. While the cosmic microwave background is the oldest light we can see, it is not the most ancient signal lingering in the cosmos. An even older, more ghostly relic permeates space, a whisper from a time when the universe was just 1 second old. This is the cosmic neutrino background. To understand how these particles could have their own background, we need to travel back to an era even more extreme than the plasma soup that produced the CMB. In the very first second after the Big Bang, the universe was so inconceivably hot and dense that even fundamental particles like neutrinos were locked in constant interaction with the primordial soup. Neutrinos are incredibly lightweight, neutral particles that interact only via the weak nuclear force and gravity, making them notoriously difficult to detect. For that first second, however, the density was so high that they were trapped, bouncing around just like the photons of light were. But as the universe expanded and cooled at a ferocious rate, a critical threshold was crossed. About 1 second after the beginning, the universe had cooled enough that neutrinos effectively stopped interacting with the rest of the particles. They decoupled from matter and began streaming freely across the expanding universe, never to be significantly disturbed again. This event happened a staggering 380,000 years before the photons of the CMB were set free. This means the cosmic neutrino background is a fossil from an epoch 1,000,000 times younger than the moment captured by the CMB, offering a direct window into the universe's very first heartbeat. Though we have not yet built a detector capable of directly observing this primordial neutrino sea, its existence is a firm prediction of the standard Big Bang model, and we already have compelling indirect evidence for its presence. The key lies in how these ancient neutrinos influence the formation of the cosmic microwave background we can measure. When the neutrinos decoupled, they were carrying away a significant amount of the universe's energy. Their departure slightly changed the timing and conditions of the later events, particularly the moment of recombination when protons and electrons combined to form atoms and released the CMB photons. Furthermore, because these relic neutrinos are so abundant, there are theoretically about 339 of them in every cubic centimeter of space. Compared to the 400 CMB photons, they exerted a gravitational influence. As the universe evolved, the gravity of this sea of neutrinos affected how the primordial plasma oscillated. The presence of the cosmic neutrino background left a subtle but distinct imprint on the statistical pattern of the hot and cold spots in the CMB, specifically by slightly suppressing the amplitude of some of the smaller scale fluctuations. When scientists analyzed the exquisite data from the Planck satellite, they found that the observed power spectrum of the CMB matches the theoretical predictions only if the effects of these primordial neutrinos are included in the calculations. It's a bit like deducing the presence of the wind by watching how it bends the branches of a tree. We cannot see the wind itself, but we can see its undeniable effect on something we can observe. In this cosmic case, the CMB is the tree, and its slight bending reveals the persistent flow of the ancient neutrino wind. Directly detecting the cosmic neutrino background remains one of the greatest technological challenges in all of physics. The problem is that these primordial neutrinos now possess incredibly low energy, having been cooled and stretched by the expansion of the universe for over 13 billion years. They are predicted to have a temperature of just about 1.95 degrees above absolute zero, even colder than the CMB. Catching one of these ghostly particles is like trying to detect the faintest sigh in a hurricane of other signals. Modern neutrino detectors, like Super Kamiok and in Japan, are superb at detecting high-energy neutrinos from the Sun or from distant supernova, but they are utterly blind to the ultra-low-energy neutrinos from the Big Bang. It would be like using a net designed to catch basketballs to try and capture individual atoms. The holes are far too big. Designing a detector sensitive enough is a monumental task that would require a radical new technology, perhaps involving the precise laser cooling of vast arrays of atoms to capture the minuscule amount of energy a relic neutrino would deposit. The pursuit, however, is considered worth the immense effort. Successfully detecting the cosmic neutrino background would be a discovery of Nobel Prize-winning magnitude, providing a direct snapshot of the universe at the 1-second mark. It would allow us to test our theories of particle physics at energies far beyond what any terrestrial particle collider could ever achieve and give us an unprecedented look into the conditions that prevailed during the very first moments of cosmic history. This pivotal moment, known as the era of recombination, marks the exact instant the universe became recognizable to our instruments. For the first 380,000 years of its existence, the cosmos was a completely different beast, a searing, opaque fog. To understand why, picture a scorching summer day where the air is so thick with humidity you can barely see a few feet ahead. Now magnify that to a cosmic scale, but instead of water vapor, the universe was filled with an ionized plasma. This means the building blocks of atoms, negatively charged electrons and positively charged protons, were torn apart by the intense heat, existing as a free-flowing, chaotic soup. In this state, light was a prisoner. A photon of light attempting to travel any distance would immediately bump into one of these free-flying electrons and be scattered in a random direction. It was a constant, dizzying pinball game where light could not travel in a straight line, rendering the entire universe a brilliant, blinding, and utterly opaque glow. There were no stars, no galaxies, no dark spaces, just a uniform, impenetrable brilliance. The shift began as the universe continued its relentless expansion. As space stretched, the energy within that space became more diluted, and the temperature began to drop. This cooling was a gradual process, but it reached a critical threshold when the universe cooled to around 3,000 degrees Celsius. At this temperature, the energy of the raging particle soup was no longer sufficient to keep electrons and protons apart. The force of electromagnetic attraction finally won out. In a process that unfolded across the cosmos, electrons were captured by protons to form the first stable, neutral atoms, overwhelmingly hydrogen. This event is what scientists call recombination, a slightly misleading name because the particles were combining for the very first time, not recombining. This transition from an ionized plasma to a neutral gas was the universe's most profound transparency event. The effect was instantaneous and dramatic. With electrons now bound safely inside atoms, the highway for light was suddenly cleared. The free electrons that had been such effective roadblocks for photons were now gone. The universe, in a cosmic instant, went from being opaque to transparent. The light that had been trapped, bouncing around for all those millennia, was finally set free. This is the light we detect today as the cosmic microwave background. That first flash, that initial burst of visibility, is the oldest picture we have. What's truly staggering to consider is that this event didn't happen in one location. It happened everywhere at once. The entire universe became transparent simultaneously, meaning the CMB radiation comes to us from a spherical shell that surrounds us in all directions. A surface of last scattering, marking the farthest point back in time we can possibly observe with light. Before this wall, the universe is forever hidden from our view, a brilliant but inaccessible past. The era of recombination didn't just create the CMB, it defined the ultimate limit of our observational horizon, giving us a baby picture that is also a fundamental boundary to our knowledge. With a brilliant flash of recombination, the universe transformed from a glowing fog into a transparent but profoundly dark expanse. The release of the cosmic microwave background didn't just give us a snapshot, it marked the beginning of an epoch of cosmic silence known as the Dark Ages. For the first time, space was truly dark. The blinding plasma had cooled into a vast, featureless sea of neutral hydrogen and helium gas, and the last embers of the primordial fire, the CMB itself, were rapidly redshifting into invisibility. This period, stretching for hundreds of millions of years, was the universe's most uneventful yet crucial chapter. There were no stars to pierce the gloom, no galaxies to cluster in the void. It was a cosmos devoid of light sources, a quiet, expanding darkness where the only significant events unfolded at an agonizingly slow pace under the silent, persistent pull of gravity. Think of it as the universe taking a deep, calm breath after the violent chaos of its birth, a long, quiet incubation period where the ingredients for everything to come were slowly, patiently assembling themselves. During this profound darkness, gravity was the sole artist at work, and its canvas was the faint blueprint of density variations imprinted on the cosmic microwave background. Those tiny wrinkles in the CMB, those slightly warmer and denser patches, were the only structures in existence. In the absolute blackness, gravity began its relentless task, tugging ever so gently on those regions of slightly enhanced density. Over millions of years, atoms of hydrogen and helium gas were slowly drawn inward. The mysterious dark matter, which had already begun to clump even before recombination, provided an invisible scaffolding, its gravitational wells deepening and guiding the flow of ordinary gas. This was an incredibly gradual process. The universe was still expanding, working against gravity's pull, and the initial density contrasts were vanishingly small. So for ages, nothing dramatic seemed to happen. It was a cosmic slow-motion ballet, a gentle sedimentation of matter into the faint gravitational valleys left over from the Big Bang. If you could have traveled through the universe during the Dark Ages, you would have encountered an almost perfectly uniform, cold, and black void, with the faint whisper of the CMB fading into the microwave background and the silent, invisible gathering of gas clouds too diffused to see with any eye. The end of this cosmic night was heralded by a monumental event, the birth of the very first stars. These weren't like the stars we see today. Known as population Roman III stars, they were behemoths, thought to be hundreds of times more massive than our Sun. They formed from pristine clouds of pure hydrogen and helium, uncontaminated by the heavier elements forged in previous stellar generations because there were no previous generations. Their formation was a watershed moment. As these first gravitational condensations grew dense enough, pressure and heat built up in their cores until nuclear fusion suddenly ignited. The darkness was broken. The first starlight flooded the surrounding neutral hydrogen gas, but this light did more than just illuminate. It began to fundamentally change the nature of the cosmos once again. The intense ultraviolet radiation from these first massive stars was energetic enough to rip electrons away from the neutral hydrogen atoms, reionizing the gas. This process, known as cosmic reionization, began to burn bubbles of ionized plasma into the neutral fog of the Dark Ages, much like turning on a light in a dark, foggy room. This reionization event, which unfolded over several 100 million years, effectively relit the universe, but in a different way. It marked the end of the Dark Ages and the beginning of the universe as we know it, filled with light-emitting stars and galaxies. The cosmic microwave background, therefore, represents more than just a first light. It is the last light of the universe's initial fiery state and the final major light source before this long, dark interlude. The journey of the CMB photons we detect today began at the wall of last scattering, and they have traveled through the entire history of the universe, including the Dark Ages and the subsequent era of reionization. In fact, a small fraction of these CMB photons were scattered one last time by the free electrons created during reionization, an effect that leaves a subtle imprint on the polarization of the CMB light, providing astronomers with a way to probe the timing of when the first stars and galaxies switched on. The Dark Ages were not an empty pause but a necessary gestation period, a quiet prelude to the dawn of light that would eventually fill the cosmos with the brilliant structures we observe today. But the story of the cosmic microwave background doesn't end with it being a passive, ancient photograph. This fossil light actively interacts with the universe it travels through, and one of the most powerful examples of this is a phenomenon that turns the CMB into a cosmic flashlight, illuminating some of the largest structures in the cosmos. This is known as the Sunyaev-Zeldovich effect, named after the two visionary astrophysicists who first predicted it. To grasp how it works, imagine you're walking through a dense fog with a bright flashlight. The light from your flashlight illuminates the water droplets in the fog, making them visible. In a similar way, the CMB acts as a uniform backlight shining across the entire universe. Now, scattered throughout this cosmic fog are immense islands of matter, galaxy clusters. These clusters are not just collections of galaxies, they are filled with an incredibly hot, thin gas, so hot that it glows in X-rays. This gas is seething with high-energy electrons, particles moving at nearly the speed of light. As the ancient CMB photons, with their characteristic low energy, pass through one of these massive galaxy clusters on their 13 billion-year journey to us, they have a fateful encounter. These low-energy microwave photons collide with the fiercely energetic electrons in the cluster's hot gas. In a process similar to a ping-pong ball hitting a speeding baseball, the photon gains a tremendous amount of energy from the much more massive electron. This interaction, known as inverse Compton scattering, gives the CMB photon a significant boost, effectively kicking it up in energy out of the microwave part of the spectrum and into a higher frequency. So, what does this look like from our perspective here on Earth? When astronomers point their microwave telescopes at a galaxy cluster, they see a very specific distortion. At the specific frequency corresponding to the CMB's peak temperature, the cluster appears neutral, but at lower frequencies, the cluster casts a distinct shadow against the CMB because photons have been scattered away from that energy range. At higher frequencies, however, the cluster appears as a bright spot because that's where the boosted photons now reside. This unique spectral signature is an unmistakable fingerprint of the Sunyaev-Zeldovich effect. The true power of this effect lies in its incredible utility for astronomers. Unlike other methods of detecting galaxy clusters, such as observing their X-ray emission or the visible light from their galaxies, the Sunyaev-Zeldovich effect has one enormous advantage: it is independent of distance. Whether a galaxy cluster is relatively nearby or at the edge of the observable universe, the distortion it imprints on the CMB is essentially the same relative strength. This is because the effect depends on the number of high-energy electrons the photons encounter along their path through the cluster. A more massive cluster has more hot gas and more electrons, creating a stronger signal regardless of how far away it is. This makes the SZ effect an unparalleled tool for taking a cosmic census of the most massive structures in the universe. By scanning the CMB map for these characteristic shadows and bright spots, astronomers can compile catalogs of thousands of galaxy clusters, including some that are so distant and faint they are invisible to other telescopes. This allows scientists to trace the growth of cosmic structure across billions of years, testing our models of how gravity assembled the universe from the smooth initial conditions seen in the CMB into the web of clusters and filaments we see today. It turns the cosmic microwave background from a static baby picture into a dynamic screen, revealing the ghostly silhouettes of the cosmic giants that stand between it and us. But the temperature map of the cosmic microwave background is only part of the story. That ancient light carries a second, more subtle layer of information encoded in its polarization, and unlocking it gives us a much deeper, more nuanced understanding of the universe's first moments. To understand polarization, think of a light wave as a tiny vibration traveling through space. Normally, these vibrations can be oriented in any direction perpendicular to the wave's path. However, when light scatters off a surface, like sunlight glinting off a lake, the scattering process can cause the light waves to vibrate in a preferred direction. This organized vibration is what we call polarization. The CMB light underwent a massive, universal scattering event at the moment of recombination, when photons bounced off electrons for the very last time before streaming freely across the cosmos. This final interaction imprinted a specific, predictable pattern of polarization on the primordial glow. This polarization isn't random, it comes in two distinct types, and each tells a different part of the cosmic story. The first and most prevalent type is called E-mode polarization. This pattern is a direct consequence of the simple act of scattering and is intricately linked to the density variations we see as the hot and cold spots in the temperature map. Imagine the primordial plasma as a choppy sea. When a sound wave, a region of compression or rarefaction passes through, it causes the electrons to move. When a photon scatters off a moving electron, the resulting polarization pattern reflects that motion. The E-mode pattern is curl-free, meaning it points directly toward or away from the hot and cold spots, like the spokes of a wheel radiating from a hub. It acts as a powerful, independent confirmation of the density fluctuations, reinforcing the story told by the temperature anisotropies. The second type, B-mode polarization, is far more elusive and carries the potential for a truly revolutionary discovery. This pattern has a swirling, curlish quality, like the water going down a drain. While some B-modes can be generated by later effects, like the gravitational lensing of the CMB light as it passes by massive galaxy clusters, there is a specific, primordial kind of B-mode that theorists get most excited about. This signal would be a direct fingerprint of primordial gravitational waves, the ripples in the very fabric of spacetime itself, generated during the violent inflationary expansion in the first fraction of a second after the Big Bang. These waves would have literally jostled the primordial plasma, creating a distinctive swirling pattern in the polarization of the CMB as the photons scattered. Detecting this primordial B-mode signal would be the smoking gun for inflation, providing our first direct evidence of the universe's hyper-fast birth and allowing us to probe physics at energy scales trillions of times higher than what we can achieve in particle colliders. The hunt for this signal is one of the most intense and challenging pursuits in modern cosmology, driving the development of incredibly sensitive telescopes placed in the driest, coldest locations on Earth, like the South Pole and the high Chilean desert, in the hopes of catching a whisper from the dawn of time. Now that we understand how the CMB's temperature map is like a photograph, it's time to look at a more subtle feature, its polarization. Think of the ancient light not just as a picture, but as a kind of cosmic film that also recorded the direction in which its light waves were vibrating. This property, called polarization, adds a whole new dimension to our baby picture of the universe. Just as polarized sunglasses reduce glare by filtering out light waves vibrating in a specific direction, the CMB light became polarized during its very last interaction with matter at the moment of recombination. As photons scattered off electrons for the final time before their long journey, that scattering process imprinted a specific orientation on the light waves, creating a faint but detectable pattern across the entire sky. Unraveling this pattern is like discovering hidden writing on an ancient manuscript, and it comes in two distinct forms that tell very different parts of the cosmic story. The first and most common type is known as E-mode polarization. The E stands for electric, as this pattern is analogous to the electric field lines around a charged object. Imagine a calm pond. If you were to press down on the water's surface with a flat board and then lift it, you would create a series of ripples that radiate outward in a symmetrical pattern. The water moves directly toward and away from the center of the disturbance. E-mode polarization is similar. It's a curl-free pattern that points directly toward or away from the sources of the disturbance in the early universe, specifically the hot and cold spots created by density variations. These E-modes are a direct consequence of the sound waves traveling through the primordial plasma. When a region was compressed by a sound wave, the electrons were moving in a specific way, and when photons scattered off those moving electrons, they acquired this radial, spoke-like polarization pattern. Scientists have detected E-mode polarization with great confidence, and it serves as a powerful, independent confirmation of the density fluctuations we see in the temperature map. It's like having two different witnesses to the same event, both telling the same story and thereby strengthening our case for what happened in the early universe. The second type, B-mode polarization, is far more elusive and carries the potential for a truly revolutionary discovery. If E-modes are like the radiating ripples from a pressed board, B-modes are like the swirling patterns you see when you drag a stick through the water or when water drains from a sink. The B stands for magnetic, reflecting its curl-like quality, while some B-modes are generated by later effects, most notably when the CMB light is gently bent or gravitationally lensed by the gravity of massive galaxy clusters and dark matter structures on its way to us. There is a specific primordial kind of B-mode that cosmologists are desperately hunting for. This signal would be a direct fingerprint of primordial gravitational waves. These aren't the gravitational waves from merging black holes that we detect today with observatories like LIGO. These would be waves generated in the first unimaginably tiny fraction of a second of the universe during the proposed period of inflation. The violent, exponential stretching of space-time itself during inflation would have sent ripples through the fabric of reality, literally jostling the primordial plasma and imparting a unique, swirling signature to the polarization of the CMB. Detecting this primordial B-mode signal would be the smoking gun for inflation, providing our first direct evidence of the universe's hyper-fast birth and allowing us to probe physics at energy scales far beyond the reach of any particle collider. The hunt for this signal is one of the most intense and challenging pursuits in modern cosmology, driving the development of incredibly sensitive telescopes placed in the driest, coldest locations on Earth, like the South Pole and the high Chilean desert, in the hopes of catching a whisper from the absolute dawn of time. The search for this primordial B-mode signal has become one of the grandest challenges in modern science, a painstaking hunt for an incredibly faint whisper buried beneath layers of cosmic static. To understand the difficulty, imagine trying to listen for a single, specific note played by a single violin in a massive orchestra that is itself playing at the volume of a distant whisper. The signal we are looking for is extraordinarily weak. the swirling pattern in the polarization created by inflationary gravitational waves is predicted to be more than 1,000,000 times fainter than the temperature variations we see so clearly in the CMB map. It is a needle in a haystack of unimaginable proportions, and separating it from other signals that can mimic it requires instruments of almost unbelievable sensitivity and precision. This challenge has driven teams of scientists to some of the most extreme environments on Earth. Foremost among these efforts is the series of experiments known as BICEP and Keck, located at the Amundsen-Scott South Pole Station. The South Pole offers a unique advantage for this work. It is the driest place on Earth. Water vapor in the atmosphere absorbs and emits microwave radiation, creating a noisy foreground that can easily drown out the faint CMB signal. The cold, dry Antarctic air provides a remarkably transparent window to the cosmos, allowing telescopes to stare for long periods at a pristine patch of sky. The BICEP and Keck telescopes are not your typical astronomical instruments. They are arrays of ultra-sensitive detectors, cooled to a fraction of a degree above absolute zero, that are designed to measure the polarization of the CMB with microscopic accuracy. They act like the most sophisticated polarized sunglasses imaginable, analyzing the precise orientation of the ancient light's vibrations. The story of this hunt has been a roller coaster of anticipation and rigorous scrutiny. In 2014, the BICEP-2 team made a dramatic announcement that sent shockwaves through the scientific community. They believed they had detected the telltale swirls of primordial B-mode polarization, a discovery that would have been a direct window into inflation. The excitement, however, was short-lived. Further joint analysis with data from the Planck satellite revealed that the signal they were seeing was almost entirely due to a much more local, though still fascinating, source: interstellar dust within our own Milky Way galaxy. This dust, composed of tiny, elongated grains, can become aligned by galactic magnetic fields and itself emit polarized light that mimics the inflationary B-mode pattern. This experience underscored the immense challenge of the task, but it also demonstrated the essential, self-correcting nature of science. It wasn't a failure, it was a crucial step that forced a more sophisticated approach, leading to collaborations that now meticulously map and subtract these galactic foregrounds. The quest is far from over. The next generation of ground-based experiments like the Simons Observatory and the planned CMB S4 project are building vast arrays of detectors that will increase sensitivity by orders of magnitude. They will scan large portions of the sky with unprecedented detail, working to distinguish the inflationary signal from every possible contaminant. Meanwhile, the future lies in space. Missions like LIGHT-BIRD, a Japanese-led satellite project with international partners scheduled for launch in the late 2020s, are being designed specifically for this purpose. By observing from the quiet, stable environment of space, free from atmospheric interference, LIGHT-BIRD will conduct a full sky survey of the CMB's polarization. Its goal is to achieve such a comprehensive measurement that it can either definitively detect the primordial gravitational wave signal or place such stringent limits that many inflationary models would be ruled out. A successful detection would be nothing short of revolutionary. It would provide our first direct evidence for the inflationary epoch, confirming that the universe really did undergo that fantastically rapid expansion. But it would do much more than that. The strength of the B-mode signal is directly related to the energy scale at which inflation occurred. Measuring it would tell us the temperature of the universe during that first split second, probing physics at energies 1 trillion times higher than what the Large Hadron Collider can achieve. It would open a window into the possible unification of gravity with the other fundamental forces, a realm of theory that is currently far beyond our experimental reach. The hunt for these ancient ripples in space-time is therefore more than a technical achievement. It is a fundamental inquiry into the very first moment of existence, a search for the trigger that set our entire cosmic story in motion. However, when we peel back the layers of the universe's oldest light, we discover that not every feature in this cosmic baby picture is a fossil from the dawn of time. In fact, the single largest and most obvious pattern visible in the cosmic microwave background is actually a local effect, a clue written not in the ancient past, but in our own motion through the present-day cosmos. This feature is known as the CMB dipole. If you look at a full sky map of the CMB, the most striking thing you'll notice after the speckled pattern of hot and cold spots is a dramatic temperature gradient. One entire hemisphere of the sky appears very slightly warmer than the other. The difference is subtle, only about 0.003 of a degree Celsius, but it's there, and it's by far the most prominent anisotropy we can measure. The direction of this warmth points toward the constellation Leo, while the opposite, cooler half of the sky lies in the direction of Aquarius. This dipole is not a whisper from the Big Bang. Instead, it is a spectacular piece of evidence that we are not stationary observers in the universe. We are on a moving platform. This effect is a cosmic version of a phenomenon you experience on a rainy day. If you're standing still in the rain, the drops fall straight down onto your head. But if you start running forward, you'll feel the raindrops hitting your face. From your perspective, it seems as though the rain is coming at you from the direction you're moving. This is known as the Doppler effect. The exact same principle applies to the CMB. The microwave photons are like a uniform rain falling on us from all directions. But because our entire solar system is moving at a tremendous velocity through space, we are effectively running into the photons coming from the direction we're headed, while rushing away from the photons coming from behind us. The photons we are moving towards appear to be boosted in energy. Their wavelengths are slightly compressed or blue-shifted, which makes them appear just a tiny bit warmer. Conversely, the photons coming from the direction we're leaving behind have their wavelengths stretched or redshifted, making them appear cooler. This creates the dipole pattern, a warm spot in our direction of travel and a cool spot directly opposite. By carefully measuring the size of this temperature difference, scientists can calculate our exact speed relative to the CMB's rest frame. The result is staggering. Our solar system is hurtling through the cosmos at approximately 370 kilometers per second, which is about 1.3 million kilometers per hour. We are being pulled in this specific direction toward a point in the sky near the constellation Leo by the combined gravitational tug of every galaxy, cluster, and supercluster in our cosmic neighborhood. This motion is our local movement superimposed on the expansion of the universe itself. It's a humbling reminder that there is no privileged center, no absolute state of rest. The CMB provides the ultimate background against which we can measure our own velocity, revealing that even as we gaze into the deepest past, we are simultaneously navigating a dynamic and ever-moving present. For all the spectacular success of the standard cosmological model, the universe's baby picture holds a few features that are deeply puzzling, features that some scientists have dramatically nicknamed the axis of evil. This name doesn't refer to a cosmic villain, but to a set of unexpected alignments and correlations on the very largest scales of the cosmic microwave background that seem challenge a foundational assumption of modern cosmology, the cosmological principle. This principle states that on large enough scales, the universe should be isotropic and homogeneous. It should look roughly the same in every direction, with no special places or preferred axes. It's the idea that we do not occupy a privileged central location in the cosmos. The anomalies lumped under the axis of evil banner suggest that on its grandest scales, the universe might not be as uniform as we thought. The heart of the mystery lies in the behavior of the largest ripples in the CMB, what scientists call the low-order multipoles. When you break down the CMB map mathematically, you can separate it into components of different angular sizes. The quadrupole, for instance, describes patterns that span 90 degrees across the sky, while the octupole covers 60 degrees. These are the very largest waves in the primordial sea. According to the standard model, these immense patterns should be oriented randomly with respect to each other and with respect to our local environment. They should point in arbitrary directions like a handful of straws tossed on the floor. Yet, when researchers analyzed the data from WMAP and later Planck, they found something odd. The planes of the quadrupole and octupole appear to be aligned with each other. Even more strangely, this shared alignment also seems to correlate with the geometry of our own solar system, specifically with the ecliptic plane, the flat disk in which the planets orbit the Sun. It's as if the universe's largest scale structures are subtly pointing back at us, a suggestion that makes cosmologists profoundly uncomfortable because it hints that our local position might not be entirely random after all. So, what could explain this bizarre alignment? Scientists have proposed several possibilities, ranging from the mundane to the revolutionary. The first and most likely explanation is that it's simply a statistical fluke. We only have one universe to observe and one CMB sky to map. In any complex data set, especially one with billions of data points, you can occasionally find patterns that look significant purely by chance. It's the cosmic equivalent of seeing a face in the clouds. The pattern is striking to our pattern-seeking brains, but it doesn't mean the clouds intentionally formed a face. Many cosmologists argue that the axis of evil is just such an illusion, a coincidence that stands out simply because we've given it an ominous name and focused our attention on it. The second possibility is that it's not a feature of the universe at all, but an artifact of our measurement, a systematic error. Despite the incredible precision of satellites like Planck, completely eliminating all foreground contamination is a monumental task. Could some subtle, unaccounted-for signal from our own Milky Way galaxy, perhaps related to its magnetic field or dust distribution, be imitating this large-scale alignment? Or could there be an unforeseen issue with the way the satellite scanned the sky or how the data was processed? Teams have searched exhaustively for such errors, and while some minor foregrounds have been identified, a smoking gun that fully explains the anomaly has remained elusive, keeping the mystery alive. Then there is the most exciting and most speculative possibility that the axis of evil is a genuine clue, a whisper of physics beyond our current standard model. Perhaps the cosmological principle, as we understand it, is an approximation that breaks down on the very largest observable scales. Some theories propose that the shape of space-time itself might be more complex than we think. Maybe the universe has a subtle, overall rotation or a preferred direction imprinted from its earliest moments. Others suggest this could be evidence of our universe colliding with another universe in the multiverse landscape, an event that would have left a bruise on the sky. While these ideas are fascinating, they remain highly speculative, as there is no independent evidence to support them. The axis of evil thus sits at a fascinating crossroads in science. It is not significant enough to force us to abandon our incredibly successful model of the cosmos, but it is persistent and strange enough to remind us that our understanding is not yet complete. It serves as a tantalizing reminder that the universe's oldest light may still hold profound secrets, challenging us to look deeper and question our most basic assumptions about the nature of reality. But if the large-scale alignments of the axis of evil challenge the cosmological principle, there is another, more localized anomaly that presents a puzzle of a different kind, a specific, chilling cold spot. Nestled in the constellation of Eridanus in the southern sky, there is a region of the cosmic microwave background that is not just slightly cooler but profoundly cold. While the typical temperature variations in the CMB are on the order of 1 part in 100,000, this particular spot is about 70 microkelvins colder than the surrounding average, a significant deviation that stands out in the statistical maps. It's not the largest structure on the CMB sky, spanning an area about 5 degrees across, roughly 10 times the diameter of the full moon, but its extreme coldness makes it a glaring outlier, a feature so unusual that it has sparked a vibrant and ongoing debate about its origin. The most straightforward explanation, and the one many scientists first considered, involves a vast cosmic emptiness known as a supervoid. This idea connects back to the journey the CMB light takes to reach us. According to a phenomenon predicted by Einstein's general relativity called the integrated Sachs-Wolf effect, photons of light can gain or lose a tiny amount of energy as they travel through evolving gravitational landscapes. If a photon passes through a region of space that is becoming more dense over time, like a growing galaxy cluster, it must climb out of a deepening gravitational well, losing energy and becoming slightly cooler or more redshifted. Conversely, if a photon travels through a region that is becoming less dense, a vast, expanding void, it will fall into a gravitational potential that is actually becoming shallower over time. This means it will emerge with a slight energy gain, making it appear warmer. But here's the twist for the cold spot. If such a void exists between us and the CMB, the effect works in two stages. As the photon enters the underdense region, it loses energy climbing out of the average density universe and into the void, which acts like a hill. Then, as it exits the void and re-enters the average density universe, it gains energy falling down the other side of the hill. In a static universe, these two effects would cancel out. However, in our expanding universe driven by dark energy, the gravitational potential of the void decays while the photon is traveling through it. This means the photon doesn't get quite the same energy boost on the way out as it lost on the way in, resulting in a net energy loss. The photon arrives at our telescope slightly cooler, and thus the region of the CMB behind the void appears as a cold spot. The hunt, then, was on to find this proposed supervoid. Astronomers have indeed identified a large underdense region in the general direction of the cold spot, a cosmic vacancy estimated to be hundreds of millions of light-years across. The problem is one of scale. The observed void, while immense, does not appear to be nearly vast or empty enough to account for the pronounced coldness of the spot. The energy imprint of the void seems too weak by a significant factor. It's like finding a small hill when the observed effect suggests we should be looking at a massive mountain. This discrepancy has led researchers to propose that perhaps the void is even larger and emptier than our current galaxy surveys can detect, a truly gargantuan emptiness that our telescopes have simply not yet fully mapped. But the difficulty in finding a void of the required proportions has opened the door for more exotic and far more speculative explanations. One of the most captivating theories proposed is that the cold spot is not a feature of our universe at all, but rather a bruise left by a collision with another universe. This idea emerges from the concept of the multiverse, which is itself a prediction of certain models of cosmic inflation. The theory suggests that our universe is just one bubble in a vast, eternally inflating cosmic foam, where countless other bubble universes are constantly being born. If another universe bubble happened to form very close to our own in the multiverse landscape, the two bubbles could have potentially collided during their initial inflationary expansion. Such a collision would have transferred energy at the boundary between the universes, creating a distinct imprint on the CMB of each bubble. In our sky, this imprint could manifest as a circular region of anomalously low temperature, a cold spot. While this idea is theoretically possible within the framework of some advanced cosmological models, it is incredibly difficult, if not currently impossible, to test. There is no independent evidence for the existence of other universes, and the cold spot alone is not enough to prove the case. For many scientists, this explanation remains a fascinating but highly speculative last resort, a reminder of how the most puzzling data can push us to the very frontiers of theoretical physics. The enduring mystery of the CMB cold spot highlights a crucial aspect of modern science. Sometimes the most interesting discoveries are the things that don't quite fit. It serves as a powerful driver for improved observations and more sophisticated simulations. New, deeper galaxy surveys continue to map the large-scale structure in that direction with greater precision, hoping to finally confirm or rule out the supervoid hypothesis. At the same time, cosmologists are refining their understanding of the integrated Sachs-Wolf effect and exploring whether other, more complex gravitational effects could be at play. The cold spot may ultimately be explained by a combination of a void and a statistical fluke, a chance alignment of a moderately underdense region with a naturally cold fluctuation in the primordial CMB. Yet its persistence as an anomaly ensures that it remains a focal point for inquiry, a testament to the fact that even our most detailed map of the infant universe still holds areas marked "Here be dragons," challenging us to look deeper and think bigger about the cosmos we inhabit. This near-perfect blackbody nature of the cosmic microwave background is more than just a curious fact. It is a profound piece of evidence that transports us directly back to a specific moment in cosmic history. To grasp why this is so significant, let's break down what a blackbody really is. Imagine an object that is a perfect absorber and a perfect emitter. It doesn't reflect any light. It soaks up every single photon that hits it and then re-radiates energy based solely on how hot it is. The classic example is a piece of iron being heated in a forge. At first, it gives off invisible infrared radiation. You can feel the heat but see nothing. As it gets hotter, it begins to glow a dull red, then a bright orange, and if it could get hot enough without melting, it would become white hot. The key point is that the color and intensity of its glow at each specific wavelength follow a precise, predictable curve that is dictated only by its temperature. This predictable pattern is the blackbody spectrum. Now apply this to the early universe. At the moment of recombination, when protons and electrons combined to form the first atoms, the entire cosmos was a searing, dense plasma. This plasma was in a state of near-perfect thermal equilibrium, meaning it was effectively a single, unified object at a uniform temperature, and just like the piece of iron in the forge, it was glowing. It was, for all intents and purposes, a perfect blackbody. The Big Bang theory made a very specific and bold prediction. If the universe began in this hot, dense state, then the leftover glow we see today should still retain that perfect blackbody signature, albeit cooled and stretched by the expansion of the universe to a temperature of just a few degrees above absolute zero. Any significant deviation from this perfect curve would have been a major problem for the theory. If the spectrum showed bumps or wiggles, it might suggest other processes were at work, perhaps even pointing to a different origin for the cosmic radiation altogether. The instrument that put this prediction to the ultimate test was the Far Infrared Absolute Spectrophotometer, or FIRAS, on board NASA's Cosmic Background Explorer satellite. FIRAS wasn't just looking at the sky, it was essentially acting as a cosmic thermometer of unparalleled precision. Its job was to measure the intensity of the CMB radiation across a wide range of wavelengths to see if it truly matched the theoretical blackbody curve. The results, when they came in, were nothing short of breathtaking. The data points from the sky aligned with the predicted blackbody curve with an accuracy that is staggering. The match was so exact that any deviations were smaller than 1 part in 10,000. To put that in perspective, it's like measuring the smoothness of a marble and finding that its surface varies by less than the thickness of a single sheet of paper over its entire area. This makes the cosmic microwave background the most perfect blackbody spectrum ever measured in nature, far more perfect than anything we can create in a laboratory on Earth. This incredible precision transforms the CMB from a mere glow into a powerful diagnostic tool. The fact that the spectrum is so perfectly smooth tells us that the universe at 380,000 years old was remarkably simple and uniform. There were no major energy injections or disturbances between the moment of recombination and the release of this light that could have distorted its thermal signature. It also places incredibly tight constraints on any alternative theories to the Big Bang. For instance, the steady-state theory, which proposed a universe with no beginning and continuous creation of matter, could not naturally produce such a perfect blackbody spectrum that fills all of space. The flawless blackbody nature of the CMB is therefore a cornerstone of modern cosmology, a silent but resounding confirmation that our universe did indeed have a hot, dense beginning, and that we are looking at the cooled embers of that primordial fire. Looking at the universe's baby picture doesn't just tell us about its birth, it also gives us a profound glimpse into its final destiny. The same precise measurements of the cosmic microwave background that allow us to calculate the universe's age and composition also contain the clues to its ultimate fate. The key lies in two critical findings from satellites like Planck and WMAP: the flat geometry of spacetime and the dominant presence of dark energy. A flat universe, as we've seen, means the expansion will continue indefinitely. There isn't enough matter and energy to provide the gravitational pull necessary to eventually halt the expansion and cause a big crunch. But the geometry alone doesn't tell the whole story. It's the nature of dark energy revealed by the CMB's detailed fingerprint that paints the most detailed picture of our cosmic future. The prevailing model, supported overwhelmingly by the CMB data, suggests that dark energy behaves like a cosmological constant, a form of energy inherent to the fabric of space itself that does not dilute as the universe expands. As the cosmos grows ever larger and more diffuse, the density of matter and radiation plummets, but the density of this cosmological constant dark energy remains steady. This means its influence becomes increasingly dominant over time. The consequence is not just continued expansion, but accelerated expansion. The universe isn't just coasting, it's pressing down on the accelerator, pushing galaxies apart at a faster and faster rate. This relentless acceleration leads cosmologists to a specific and somewhat chilling forecast for the cosmos, the heat death, also known as the Big Freeze. In this distant future, the story of the cosmic microwave background itself becomes a central character in the cosmic endgame. Remember, the CMB is the cooled and stretched remnant of the universe's fiery beginning. That cooling and stretching is a direct result of cosmic expansion. As the fabric of space continues to stretch at an ever-increasing pace, the wavelengths of the CMB photons will be stretched even further. Their temperature, already just a few degrees above absolute zero, will continue to plummet. Billions of years from now, the CMB will have redshifted out of the microwave band entirely, its photons becoming so low in energy that they will be virtually undetectable. The universe's oldest light will effectively fade to black. The same will happen to the light from all stars and galaxies. As the expansion accelerates, distant galaxies will be pushed beyond our observable horizon, their light unable to ever reach us again. Eventually, all galaxies outside our local gravitationally bound group will disappear from view, leaving an isolated island of stars in an ever-darkening, empty void. The final stages of the heat death are even more profound. Over trillions of years, the fuel for star formation will be exhausted. The last stars will burn out, leaving behind cold stellar remnants, white dwarfs, neutron stars, and black holes. Even these remnants are not eternal. Through a process predicted by quantum mechanics, even black holes are thought to slowly evaporate over unimaginable timescales, radiating away their mass until they too vanish. What remains is a universe that is utterly dark, incredibly cold, and almost perfectly empty. It will be a near-perfect vacuum where the temperature approaches absolute zero and no meaningful energy gradients exist to power any process or sustain any form of life. The cosmos will have reached a state of maximum entropy, a final, uniform equilibrium where effectively nothing ever happens again. This vision of the future, dictated by the data encoded in the ancient CMB, is both awe-inspiring and humbling. It suggests a cosmic story with a dramatic beginning, a vibrant middle age of structure and life, but a quiet, fading conclusion. Yet, it's important to remember that our understanding is based on the physics we know today. The nature of dark energy is still one of the greatest mysteries in science. Could it evolve over time in a way that leads to a different fate, like a big rip where the fabric of spacetime itself is torn apart? The continued study of the cosmic microwave background, especially its polarization and its interaction with large-scale structure, will be crucial for refining these predictions. For now, the universe's first light serves as our most reliable crystal ball, telling a story that stretches from a brilliant flash of creation to a silent, cold, and eternal dusk. Beyond its role as a map of our cosmic origins, the cosmic microwave background has become one of the most powerful tools we have for probing the very laws of physics themselves. It functions as a colossal, natural laboratory, allowing us to conduct experiments on scales and at energies that are utterly impossible to recreate on Earth. The incredible precision of measurements from satellites like Planck has turned the subtle patterns in this ancient light into a stringent test for any new theory that attempts to go beyond our current understanding, particularly the standard model of particle physics. This model, while brilliantly successful at explaining the world of subatomic particles, is known to be incomplete. It doesn't account for gravity. It offers no explanation for the dark matter that fills the cosmos, and it leaves the nature of dark energy as a total mystery. The CMB provides a unique window into these frontiers, imposing strict limits that any new theory must obey. One of the most significant ways the CMB constrains new physics is through its precise measurement of the number of neutrino species. The standard model tells us there are 3 types of light, left-handed neutrinos. But what if there were more, theories proposing a 4th, sterile neutrino, a particle that interacts only via gravity, and not the other forces, have been considered to explain certain anomalies in particle physics experiments. The presence of such an additional neutrino species would have left a clear fingerprint on the early universe. More neutrinos mean more radiation energy density in the primordial plasma. This extra energy would have altered the way gravity competed with radiation pressure during those crucial first few 100,000 years, changing the characteristics of the sound waves that produced the CMB's hot and cold spots. The detailed power spectrum measured by Planck is exquisitely sensitive to this effect. The data firmly rules out the existence of a full additional sterile neutrino, placing a tight upper limit that strongly supports the 3-neutrino picture of the standard model. Furthermore, the CMB allows us to weigh the neutrinos we know exist. For decades, neutrinos were thought to be massless, but we now know they have a tiny, non-zero mass. The CMB, combined with measurements of the large-scale structure of the universe, allows cosmologists to put a cap on the sum of the masses of all 3 neutrino species. The latest results suggest this total mass must be less than about 0.12 electron volts. To grasp how precise this is, an electron volt is a unit of energy and mass so small that a single electron has a mass of about 500,000 electron volts. The CMB is helping us weigh the lightest known particles in the universe with astonishing accuracy, a measurement that pure particle physics experiments struggle to achieve. The CMB also serves as a critical testing ground for the properties of dark matter. While we know dark matter exists due to its gravitational effects, its fundamental nature remains one of the biggest puzzles in science. Is it a single type of particle like a WIMP or a whole family of particles? Is it completely cold and slow-moving, or could it have a small, intrinsic warmth, meaning its particles moved at a significant fraction of the speed of light in the early universe? The behavior of dark matter in the infant cosmos directly influenced the growth of the tiny density fluctuations we see in the CMB. Cold dark matter, which moves sluggishly, is excellent at clumping together on small scales from the very beginning, providing the gravitational seeds for structure formation. If dark matter were warmer, with particles moving faster, they would have streamed freely across the early universe, washing out small-scale fluctuations and delaying the formation of the first galaxies. The sharp, well-defined peaks in the CMB power spectrum, especially the third peak, which is very sensitive to the amount of matter, strongly favor the cold dark matter model. The data is so precise that it effectively rules out models where dark matter was warm enough to significantly suppress small-scale structure, narrowing down the possible characteristics of this mysterious substance. Perhaps one of the most mind-bending applications of the CMB is its use as a cosmic clock to check if the fundamental constants of nature have changed over billions of years. The fine structure constant, for example, governs the strength of the electromagnetic force. What if this number was slightly different 13 billion years ago? The physics of the primordial plasma at the moment of recombination depended critically on the values of these constants. A change in the fine structure constant would alter the way photons scattered off electrons, which in turn would change the relative heights of the acoustic peaks in the CMB power spectrum. By comparing the observed spectrum with detailed theoretical predictions, scientists can search for any evidence that the laws of physics were different in the past. The results from Planck show no evidence for such a variation. The constants appear to have been constant, at least to within a few parts in 10,000, over the vast majority of cosmic history. This is a profound finding, suggesting that the fundamental rules of the universe are stable and universal, providing a firm foundation for all of cosmology. By using the universe's oldest light as a benchmark, we can perform a type of experimental physics that spans billions of years, testing the very fabric of reality in a way that no terrestrial laboratory ever could. With the phenomenal success of Planck, you might think we've learned all we can from the universe's oldest light. But in many ways, the most exciting chapter of cosmic microwave background research is just beginning. The current maps, for all their stunning detail, are not the final word. They are the foundation upon which a new generation of even more ambitious telescopes is being built. These next-generation instruments are not simply making higher-resolution pictures. They are embarking on a targeted hunt for the most subtle signals buried within the ancient glow, signals that could fundamentally rewrite our understanding of physics. The future of CMB science is focused with laser-like precision on one primary goal: definitively measuring the polarization of the CMB, and within that, finding the holy grail of cosmology, the signature of primordial gravitational waves. Leading this charge on the ground are colossal international projects like the Simons Observatory and its planned successor, CMB S4. The Simons Observatory, currently under construction in the high, dry Atacama Desert in Chile, represents a massive leap in capability. It will deploy an array of several telescopes equipped with over 50,000 detectors, a number that dwarfs previous experiments. This army of sensors, chilled to a fraction of a degree above absolute zero, will scan the sky with unprecedented speed and sensitivity, measuring the polarization of the CMB with a precision we can only dream of today. But this is merely a precursor to CMB S4, a project on a truly monumental scale. Imagine hundreds of thousands of detectors spread across multiple telescopes in both Chile and the South Pole, working in unison to create the most sensitive map of the CMB ever attempted. The goal of CMB S4 is to improve the sensitivity to the faint B-mode polarization signal by an order of magnitude compared to current efforts. This is not an incremental upgrade. It is a transformation in our ability to listen to the whispers of the early universe. These ground-based observatories benefit from established infrastructure in the world's best observing sites, but they must still peer through the filter of Earth's atmosphere. While the dry air at these locations is remarkably transparent to microwaves, even the faintest atmospheric noise poses a challenge when searching for a signal that is millions of times fainter than the primary CMB temperature variations. This is why the ultimate future of CMB research likely lies back in space. Free from the murky interference of our atmosphere, a space-based telescope can observe the entire microwave sky with perfect clarity and stability. Several proposed missions are vying to make this a reality. The Japanese lead light bird mission, scheduled for launch around 2030, is specifically designed as a dedicated polarization explorer. Its objective is to conduct a full sky survey of the CMB's polarization with a sensitivity that would allow it to detect the primordial gravitational wave signal even if it is incredibly faint. By operating from the second Lagrange point, the same quiet orbital location used by the James Webb Space Telescope, Light Bird will be able to stare deeply into the cosmos without the daily and seasonal cycles that affect ground-based observations. Other concepts being studied by NASA and the European Space Agency envision even more advanced CMB satellites that could follow in the next few decades. These missions would combine the pristine environment of space with detector technology matured by projects like CMB S4, potentially creating a map of the CMB so clean and detailed that it would reveal not just the inflationary B modes, but also a host of other subtle effects, such as the polarization imprinted by the very first stars and galaxies during the epoch of reionization. The scientific payoff from these future experiments will be transformative regardless of what they find. A definitive detection of the primordial B-mode polarization would be one of the most significant discoveries in the history of science. It would provide direct, incontrovertible evidence for cosmic inflation, confirming that the universe underwent that fantastically rapid expansion. But it would do much more than just validate a theory. The strength of the B-mode signal is a direct measure of the energy scale at which inflation occurred. Detecting it would tell us the temperature of the universe during that first split second, opening a window into physics at energies 1 trillion times higher than what the Large Hadron Collider can achieve. This would allow us to probe theories that seek to unify gravity with the other fundamental forces, realms of physics that are currently entirely theoretical. Conversely, if these next-generation experiments fail to find the signal, placing even more stringent upper limits on it, that would be equally revolutionary. It would rule out a wide swath of the simplest and most popular inflationary models, forcing cosmologists back to the drawing board to conceive of more exotic and complex scenarios for the universe's birth. The future of CMB research is therefore a win-win scenario for science. Whether these telescopes find the signal or firmly rule it out, they are guaranteed to deepen our understanding of the cosmos, pushing our knowledge from the earliest moments of time to the farthest frontiers of fundamental physics. And so, after this incredible journey through 30 facts, we arrive at a final, humbling realization. This faint cosmic static is more than just data. It is our shared cosmic heritage, a direct, tangible message from the dawn of time that connects every single one of us to the origin of the universe. The light from the cosmic microwave background doesn't just come to us from a distant satellite. It perpetually rains down on Earth from every direction in the sky. And in a wonderfully poetic twist, you don't need a multi-million-dollar space telescope to detect its presence. If you own an old-fashioned analog television set, one with a rabbit ear antenna, you can witness a tiny piece of this ancient story yourself. Tune that television to a channel where there is no broadcast signal. The chaotic black and white visual snow and the accompanying hiss of static that fill the screen are not purely random. A small percentage of that signal, roughly 1%, is caused by photons that have been traveling for 13.8 billion years. That flickering gray fuzz contains within it the literal afterglow of creation. Every time you saw that static as a child, you were looking at a fragment of the universe's oldest light. This means that for decades, in living rooms all around the world, humanity has been passively receiving a transmission from the Big Bang itself, long before we even knew what it was. We are all, in a small but profoundly real way, constantly in touch with our cosmic beginnings. This connection transforms the cosmos from an abstract, distant concept into something deeply personal. The atoms that constitute your body, the calcium in your bones, the iron in your blood, were forged in the hearts of long-dead stars, scattered across space by supernova explosions, and eventually coalesced here on Earth. But the story of those atoms begins even earlier. The very hydrogen atoms that form the water in your cells were created in the primordial nucleosynthesis that occurred just minutes after the Big Bang. And the gravitational seeds that guided those atoms into the stars that forged the heavier elements were the infinitesimal density fluctuations imprinted on the cosmic microwave background. You are not just living in the universe, you are a product of its entire history, a direct descendant of those first quantum ripples. The CMB is the ultimate family photo, the background against which our entire existence has played out. It is the foundational canvas upon which the intricate tapestry of galaxies, stars, planets, and life was eventually woven. To study this ancient light is to read our own origin story, to understand the initial conditions that made our reality possible. Ultimately, the story of the cosmic microwave background is a testament to human curiosity and ingenuity. From an annoying hum in a New Jersey antenna to the exquisitely detailed maps from Planck, our quest to understand this whisper has fundamentally reshaped our place in the cosmos. It has answered ancient questions about our origins while opening breathtaking new mysteries about dark matter, dark energy, and the very first instance of time. This faint glow reminds us that the universe has a history, a narrative of transformation from a hot, dense beginning to the complex and beautiful cosmos we see today. It invites us to look up at the night sky with new eyes, not as a static ceiling of lights, but as a dynamic, evolving storybook. The dark spaces between the stars are not empty, they are filled with the faded light of creation, a constant, gentle reminder of where we came from. The universe's oldest light is more than a scientific specimen. It is a beacon from the past, illuminating our path to understanding the grandest story ever told. The story of everything. From the serendipitous discovery of a persistent microwave hum to the ultra-high-definition maps revealing the universe's fundamental blueprint, this journey through the cosmic microwave background reveals a story more incredible than any fiction. We've seen how this ancient light is not a mere relic but an active cosmic tool, a flashlight illuminating galaxy clusters through the Sunyaev-Zeldovich effect, a fossilized sound wave recording the universe's first notes, and a precise yardstick measuring the flatness of spacetime itself. It has handed us the recipe for the entire cosmos, showing us that the familiar world of atoms is a mere 5% of reality, while the mysterious dark matter and dark energy dominate the rest. This faint glow has confirmed our universe's explosive beginning, provided compelling evidence for a fleeting period of hyper-fast inflation, and even offered a forecast for our cosmic destiny, a quiet, cold fade into equilibrium. Each fact is a thread in a grand tapestry, weaving together a narrative that stretches from an unimaginably hot, dense beginning to the structured, evolving cosmos we call home. Ultimately, the profound significance of the cosmic microwave background is that it transforms our place in the universe from passive observers to active readers of our own cosmic story. This light is our collective inheritance, a signal that has been arriving continuously since long before our planet, our sun, or even the first stars existed. By learning to decode its subtle patterns of temperature and polarization, we are not just studying an abstract scientific concept, we are uncovering the initial conditions that made our existence possible. Those tiny quantum fluctuations, magnified by inflation and frozen into the CMB, are the very seeds from which galaxies, stars, planets, and eventually life itself would grow. You are a direct product of those ancient ripples. Understanding this light is therefore an act of self-discovery, a way to comprehend our own origins on the grandest possible scale. It connects every one of us to the moment of creation, reminding us that we are not just living in the universe, but that the universe is living through us. So the next time you look up at a quiet, dark night sky, remember that the emptiness is an illusion. It is filled with the faded afterglow of the Big Bang, a constant, gentle presence connecting you to the very beginning of time. The story of the CMB is a testament to human curiosity, our ability to take an annoying bit of static and, through perseverance and ingenuity, unravel the deepest secrets of existence. It is a story that is far from over, with next-generation telescopes poised to hunt for the whispers of primordial gravitational waves, promising to reveal even more about those first fleeting moments. We would love to hear which of these 30 facts reshaped your view of the cosmos the most. Was it the accidental discovery by Penzias and Wilson? The idea that the largest structures grew from quantum jitters, or the humbling reality that we are all bathed in this ancient light? Let us know in the comments below. And if you enjoyed this deep dive into the universe's oldest light, be sure to subscribe and hit the notification bell so you don't miss our next journey into the mysteries of space.